All right, thanks for tuning in. I'm Sebastian. I'm a software engineer at Isovalent. We are a security and networking company who is building Hubble, which I'm going to talk about today, and Cilium. And so the talk today is about Hubble, an eBPF-based observability tool for Kubernetes. So what does observability in Kubernetes mean? What are the kind of questions that Hubble tries to answer? Kubernetes is kind of a complex beast. So from different perspectives, there can be different questions that we might want to ask. So if I'm an application developer, I would, for example, like to know what kind of services my application is depending on. I would like to know which HTTP endpoints or which gRPC or Kafka calls are being made from my application. And of course, I also want to know the performance characteristics of these calls. If I'm an operations person, I might have a different set of questions I want to ask my tool. So if I'm an operations person, I might be more interested in the network communication. I want to know if the network communication is failing. And if it is failing, I want to know the reason why. Is it a problem with the application? Is it a problem with the network? If it is a problem with the network, I would like to know why and on which layer these problems occurred. And if I'm a security person, I might have a different set again that I would like to have answered. So, for example, if I have a Kubernetes cluster which has network policies enabled, I would like to see if these network policies are being enforced and what connections are being dropped. If there's services that are being accessed by outside entities or that are connecting to outside entities, I would also like to know what services are being accessed and what outside entities are being accessed. So these are the kind of questions that Hubble tries to answer. And the tool it has chosen to implement its functionality is eBPF. So I briefly want to talk about eBPF, what it is, and how we use it. So eBPF stands for Extended Berkeley Packet Filter. It's a Linux kernel feature that allows you to attach small programs to the Linux kernel in a secure and efficient manner. I will, again, briefly explain what this means in more detail in a second. So eBPF allows us to attach programs to the kernel on various attachment points. So on the slide here, I have an example program that is invoked whenever there's an outgoing packet on a certain interface. So I can attach this program, for example, on the socket layer, and whenever there's a new packet going out on that interface, this eBPF program will be invoked. So it's an event-driven mechanism. And this sample program here, it's written in C, but it will be compiled to bytecode. This example program will extract the Ethernet and IP header and then display us the source and destination IP address of this packet, as well as the protocol of the payload that is being transported. And while BPF originates in the networking space, it has been extended to support quite a few other attachment points. So we can, for example, also attach BPF programs to system calls. This is a common use mechanism, for example, to implement sandboxing, where we can inspect system calls and maybe block or even rewrite them if needed. And the kernel also has some additional capabilities as well to inspect user space processes, but there's also layers deeper down in the network stack where we can access BPF probes. And these days, you can even push down BPF programs to the network card, and the network card will invoke your BPF program whenever it sees a new packet. So why do we want to use this technology in Hubble? Why do we want to use this technology for observability? And the biggest reason is that it is completely transparent to the application. The application doesn't know that eBPF is being used at all. So this means we don't have to modify the application, which is important, especially when we are troubleshooting issues that we have never seen before, where we could not modify the application ahead of time to make sure we cover that use case. eBPF is also, because it's dynamic, it has a minimal overhead, so we can attach probes only when we need them, and we can enable and disable them whenever we want to get deeper visibility. eBPF is already widely available, so there's a few large-scale users. I have a few names there on the slides that are already using it in production in quite large clusters. And it's also widely available on most cloud providers. So Hubble, for example, only requires Linux 4.9 to run. If you are interested more in eBPF and its history and how it came along, I highly recommend you check out the KubeCon talk by my coworker Daniel. He's also one of the BPF subsystem maintainers in the Linux kernel as well. So how would you use an eBPF program? I have a small example here on this slide. So eBPF programs are typically loaded by a user space agent. This is a user space program that is taking the C program. So we have the C program there in the middle that we want to attach, in this case, to the socket layer of the Linux kernel. So what the agent does is it will take this C program and compile it to bytecode and then load the bytecode. So eBPF is always bytecode, similar to, for example, how JavaScript works. So this bytecode is then loaded into the kernel. And the first thing the kernel does is verify that this bytecode does not do anything dangerous. By that, I mean that it terminates, so it cannot block the kernel, and that it doesn't crash the kernel or access any data structures that it is not supposed to access. Once we know that this program is safe and cannot crash the kernel, we will then optimize it using a just-in-time compiler, which will take the bytecode and emit machine code, which is basically as optimized as a kernel module. And so once we have the machine code, we can attach this machine code to our attachment point, in this example, the socket layer of the kernel. And once we have attached the BPF program, it will get invoked for each, in this case, outgoing packet that, for example, a process will emit by using the send system call. So whenever there's a send system call, the packet will be processed by the Linux kernel, and we will be informed about each outgoing packet. And we can then either decide to, for example, log it for observability purposes, but we can also implement things like firewalls or other policies. A nice feature about BPF is that these programs that we attach to the kernel, they can have state, and the state is managed by what we call BPF maps. There's different kinds of maps available. The kind of most common one is a basic hash table, but there's other one like ring buffers that we can use to stream events. And so this is used to communicate with our user space agent that loaded us into the kernel. And the BPF map can be used for transferring of state. It can be used for configuration. So for example, we can add filter lists to the program using eBPF maps, but it's also used to send down events from the BPF program to the agent, and the agent can see what the BPF program is currently seeing and doing. So two technologies that use eBPF quite heavily to implement networking on Kubernetes are Cilium and Hubble. And the two come together. So Cilium is in its core a CNI, a container networking interface, which means that it implements the pod-to-pod network connectivity on your Kubernetes cluster. It is the piece of software that is responsible for forwarding your pod-to-pod traffic. But Cilium has a few additional features on top of that, such as, for example, service-based load balancing. So it comes with a kube proxy replacement, which completely replaces the kube proxy, no port, and load balancing implementation. But Cilium also has additional features like it supports Kubernetes network policies, which means that we can enforce network traffic rules. We can block certain pods from communicating with each other. And Cilium also provides node-to-node encryption. Hubble, so while Cilium kind of manages the network connectivity in our cluster, Hubble allows us to observe it and more. So it's the network observability part of Cilium, and it can produce things like service dependency maps. It has a troubleshooting API that we can use to dive deep into what's currently going on. And it also provides us with mechanisms to obtain metrics and to do monitoring. So Hubble and Cilium are quite intertwined. We released a preview of Hubble late 2019, where we released the basic functionality of metrics and the command line tool, as well as a preview of our graphical user interface. This was built for Cilium 1.6. So in Cilium 1.7, we open sourced the UI, and Cilium 1.7 is the first release of Cilium to also contain additional features specifically designed with Hubble in mind. So it supports visibility annotation, and it also gives Hubble more metadata about the trace events that it emits. In March, we had our first kind of proper release where we also provide some API stability. And Cilium 0.5 is also the last release that we support for Cilium 1.7, which is kind of where Hubble and Cilium are kind of separate entities. Because in Cilium 1.8, which was released in June 2020, we integrated Hubble and Cilium even closer together. So the Hubble API is now directly integrated into the Cilium agent, which allows us much better performance. And the release itself also had a bit more stability improvements in terms of the UI and scalability improvements in terms of the UI. And Hubble 0.6 also comes with initial support for Hubble Relay, which allows you to do cluster-wide troubleshooting as well. So how does Hubble use eBPF? As I've mentioned before, in Cilium 1.8, Hubble and Cilium are both part of the same user space process, the Cilium agent, which is responsible for submitting eBPF programs to the kernel to implement all the features that I've mentioned. So Cilium attaches BPF programs to all Kubernetes pods that are in the system or on the local node. And it subscribes to the Kubernetes API to be informed about Kubernetes resources such as existing pods, existing services, nodes that have been added to the clusters, and of course, network policies that Cilium needs to enforce. So it takes this data obtained from the Kubernetes API and writes them into BPF maps, which are then accessed by the eBPF data path. So if a pod wants to connect to either a pod on the same node or to entities on a remote node, it will have to go through the eBPF data path. And so the eBPF data path will take the incoming connection, will inspect the packages, see if it has to do some load balancing. So it will access the service map to find service backends and frontends and maybe rewrite the packet even. It will annotate identities. So it will check the source and destination IP and see if these are known identities, which is important for policy enforcement. So policy enforcement, in the policy map, we will see whether the source identity is allowed to access this destination identity. And while the data path is working, it will emit trace and drop and policy events at certain points in the code. And these events are also pushed into a BPF map, the event BPF map, which is a ring buffer, which is read by a Hubble instance running inside the Cilium agent. So this Hubble instance will collect these networking events, store them in a historic buffer, and expose it via gRPC and metrics. And these can then be accessed by other Hubble components, such as the clients that we have, like the graphical user interface, and also Prometheus. So to see a bit more details of this, we have the Hubble UI, which is the graphical user interface, which will give you service dependency maps. I will have a demo later with the UI to see how it actually looks like in practice. The UI also allows you to display flows, filter flows, so you can only see a subset of flows if you're interested. And it also is able to display you Cilium network policies. The command line interface is a bit more advanced troubleshooting, so it gives you all the details, the details that are available in a flow. You can filter the output quite extensively. We have quite a few filters that are implemented, and the command line utility also has a JSON output that you can use for scripting. And so these are the kind of the two troubleshooting tools that we have, but we also provide metrics. So Hubble has built-in metrics for both operations and application monitoring purposes. I will later show a bit more how they work and what they provide, but basically they can be used in your typical Grafana and Prometheus stack to monitor the things going on in your cluster. So the Hubble API, what does it provide? The Hubble API provides access to recent flows that occurred in the cluster. Typically, it's 4K events that are stored in each node, but this is configurable. You can also stream currently ongoing flows as well. You can submit filters and only see the flows which match a filter, or you can exclude flows based on a filter. And in Cilium 1.8, we also added a new feature for cluster-wide visibility. So the Hubble API is re-implemented by this component called Hubble Relay, which you can talk to, and it will push down the filters to all the different nodes to make sure that you can find all the flows occurring in your cluster. And as I've mentioned, the API is accessed by both the CLI and the UI. So what does the API provide in details? It has a few information that are obtained directly from the eBPF data path. So flow metadata such as Ethernet, IP headers, TCP flags, but also things like HTTP and DNS traffic, as I will show that in a second. It annotates Kubernetes information such as pod names, labels, service names, node names, and if available, it will also match the domain names and will show you the domain names of either the source or destination of a certain flow event. And we also attach a few Cilium-based information such as security identities, drop reasons, and policy verdict decisions. So in the screenshot there, you see how the CLI looks like. So we have a small 4-pod example. This is stolen from the Cilium Getting Started guide. And we see that we can use Hubble Observe, the CLI, to filter by label. So in this case, I'm doing a class equals X-Wing label filter to only see events from pods emitted matching this filter. And we invoke it in follow mode, which means we see all the live flows. And in this example, we see that the X-Wing pod is accessing core DNS to do a DNS lookup. We see this on port 53, which is UDP traffic. And this is then followed by some HTTPS request to an outside entity. In this case, it's apparently accessing disney.com. So we see the full TCP connection, including the shutdown as well. And at the bottom there, we see how it looks like if a pod is accessing something which it is not supposed to. So in this case, the X-Wing pod, managed by the rebels, is trying to access the Death Star, which is managed by the Empire. And the Empire has installed a policy that doesn't allow this flow to go through. So Hubble informs us about this drop as well. All the information that I've showed you in the previous slide is information obtained directly from the eBPF data path, but Hubble can go deeper. If we opt into L7 visibility, we can also see more details. So what this will do is that Cilium, if we annotate a pod, so in this example, we annotate the TIE Fighter pod with a visibility annotation, which says that we are interested in outgoing traffic, outgoing HTTP traffic on port 80. So as soon as we do this, Cilium will transparently insert a proxy between the pod and all outgoing endpoints. And this then allows Hubble to observe the metadata emitted by the Envoy proxy in this case. So we have support for HTTP, DNS, TLS, Kafka, but the Envoy proxy can also be extended with different protocols. And we can then access this data from Hubble. As we can see in the screenshot there, we are using the CLI to filter based on so we're filtering from the TIE Fighter pod, which we just annotated, and we tell it to only display us HTTP responses, which have status code 200, and we output this as JSON. So using JQ, we can actually then parse this JSON, and in this case, I'm just extracting the L7 information, and we see all the metadata that Hubble has access to, which is things like the latency, but also details like which URL was accessed and the HTTP headers. So in this case, we see that the request was apparently made by curl. So this is what the API can do, but as I mentioned, Hubble also provides metrics. So these are based on the open metrics format. Hubble exposes a metrics endpoint on each node, which then can be scraped by Prometheus. There is a ton of built-in metrics that I'm not able to show all of them today, but we have metrics for HTTP details. So the L7 visibility details can also be integrated to metrics. We have metrics for DNS requests and responses. We have metrics for TCP flags. We have metrics for ICMP and many, many more. We also provide dashboards for Grafana. So you can just use our example dashboards to try this out. And the metrics can be enabled and disabled on a metric by metric basis. And it's also quite easy to write new metrics as well if you want to. So this is kind of the overall overview of Hubble. So let's see how it looks like in action. So what I have here is a Kubernetes cluster running Cilium and Hubble. So we have a 3-node cluster running Cilium, and as well as Hubble and Hubble relay, and UI. And if we check the status output of Cilium, we will see that we can access, or that Hubble is enabled, and that we can also access metrics as well. So in this cluster, I will now access Hubble UI. I've done a port forwarding already ahead of time. So now we see the Hubble UI. This is how it looks like. It displays a service map for this. This is an example application, and it generates the service map only by the flow events emitted by Hubble. So in this case, we see an application which is kind of a job portal where we have recruiters which are posting applicants, and we have a job posting pod which is creating new jobs and listing them, and people applying to jobs, both via an API, which on the backend then access Elasticsearch. We have a crawler, which is crawling Twitter to find CVs and kind of information and loads them into a Kafka topic, which Kafka, as we know, also needs Zookeeper. So we kind of see the service dependencies here quite easily. And we also see which endpoints are being accessed thanks to L7 visibility. We have the policy view, so we can see that there's two policies, one on the Elasticsearch and one of the crawler pod. And so for the crawler, we seem to have a policy for egress or for outgoing traffic. And we see that the crawler pod is only allowed to access Twitter and the loader pod that it needs to access, and the DNS for kubedns as well. So this makes sure that the crawler pod only accesses the network connections that it is supposed to. And we see indeed in the service map that we only have flows going to Twitter and the loader. So now let's try to see what happens if you actually try to access an entity which is not part of the policy, which will be blocked by the policy. So in this example, I'm now kubectling into the crawler pod, and I'm accessing a curl request to the Cilium.io domain. And we will see that after 3 seconds, this will time out because the policy does not allow it. And indeed, we can double check this by using the Hubble CLI. So I will ask for dropped flows for the crawler pod, and we will see that we have policy denied events coming in. We can also see this in the UI. So in the UI, we have the flow view as well. And if you refresh the page here, we will see that the dropped flow will also occur. If you filter by crawler pod, we can see the dropped flow there as well. So this is kind of the UI and the service map and the information it provides. Another thing that Hubble provides are metrics. So on the second tab there, I have Grafana already open. These are the metrics that Hubble provides. So we can, for example, see the general metrics that Hubble produces. We see the amount of flows per second per node. We see what kind of flow types that we have. We see also things like drop reasons and so forth. So these are all generic metrics that you can enable and disable based on your preferences. So we have drop forwarded flows. We can also see where trace events are being emitted. And here, for example, we have the drop reason. And if you look really closely, we can see that there has been a slight increase in policy denied drop reason, which is exactly the flow that we just tried to emit on the pod. We also see other information like TCP, ICMP, UDP information. So there's a ton of metrics that you can collect. I'm not going into details here right now, but there should be something for both application, operations, and security persons here. So let's take a look at an L7 metric. So these are HTTP metrics being collected in the whole cluster. So this is all HTTP metrics for all the HTTP traffic in the cluster that we have visibility into. So we see things like methods. We see that most requests seem to be successful, so almost no 500s. And we also have latency information. So we see the medium latency, which seems to be below 10 milliseconds. And you have the tail latency, which in this case starts to look a bit weird, right? So in the tail latency, we seem to have these spikes. And if we look closely, we see that there's, so this is bucket based. So we see that the up to 200 millisecond bucket seems to have quite a few spikes that are occurring maybe every 30 seconds or so. So there seems to be a performance problem with our application. Something is a bit fishy in this application, or something is fishy in our cluster, and we want to now use Hubble to figure out what exactly we want to do. So let's start to investigate. The way I will investigate this is using the Hubble CLI, using the JSON output. So this is a jQuery which will sort the all HTTP and requests by latency, and we're only showing the maximum latency for each URL. And so we see here that indeed that there's two endpoints, job endpoints in the core API, which seem to have quite a high latency, while the rest here seems fine. There's only two endpoints that have this really weird high maximum latency. So since this is on the core API, let's start to investigate this. So we can filter by recent traffic, say for the last 3 minutes. We want to see all traffic for the core API part. I'm using a label filter here, and I'm just using less to kind of be able to grab the output. So this is the Hubble output again. We see all the events emitted by the core API pod, and I grab for the endpoint. So here's a request that seems to have only 2 millisecond latency. That's fine. And if I go to the next one, I now see there's now a request which has 106 millisecond latency. So this is one of the degraded requests. So we have the request coming in up there, and then 100 milliseconds later, we see the response going out at the bottom right there. So let's see what happens in between. So we seem to have a bit of unrelated traffic from the proxy. This is fine. The TCP flags look fine. Nothing too conspicuous here. So this is just a request coming in from the proxy and being sent to the core API. But then we see on this line here, we see the core API trying to access memcached. So it seems to be using caching. And we see that the TCP flags indeed for the response are a reset. So this connection is being dropped. So it seems like the core API is unable to access the cache for some reason. And we see then the Elasticsearch request going out to the backend to fetch the information from the backend instead of the cache. So let's see kind of what connections we have to this memcached instances. So I've copy pasted the domain for the memcached service. So I can again write with the CLI, I can write a filter where I say, show me all the traffic to this domain, and this will show me all the traffic to the domain. And we see that there's a few different connections, but all from the core API. Now I'm doing a second request as well, which will get rid of the name resolution and just show us the raw IPs. And so here we don't have the annotations anymore. This is just the raw data. But if you look at this, we see the requests, the resets being emitted there. And so if we look more closely, we can actually see that the reset only seems to occur on IP point 23. The other destinations like point 25 and point 24 seem to be fine. So let's quickly double check what kind of IPs are associated with this domain. So we can filter by DNS request, and indeed we see that we have 3 IPs associated with the memcache, and one of these IP is the .23, which seems to be behaving really, really strangely. So let's see if we can reproduce this. Let's see if there's really a problem. So now I'm kubectling into the core API pod, and I'm just accessing the IP directly on the memcached port. And if we execute this command, we should see whether or not we can access memcached. And indeed, it seems to fail for this particular instance. So let's try a different one. The other one's worked. So we have established the root cause now that indeed point 23 seems to be inaccessible. So we have, let's check again. We have 3 backends for the memcached. And so we've established that there seems to be a problem with one of these nodes, and we can check that. And in this case, of course, I know what the reason is because this is a demo that I've prepared. So let's SSH into this instance and see what's going on. So I will SSH into this faulty memcached pod and show me the list of containers that are currently running or have been stopped. So if I use Docker PS on that instance, I see that there's indeed a memcached that has been turned off an hour ago almost. So that would explain why we see dropped connections. So I can now start this container again by just starting the Docker container. And once the container is up again, we can now verify whether the connection works. So again, I'm using kubectl to directly access the pod, and now the instance is up. So a few minutes later, we can now check again how things are. So we still have access to the memcached. That seems to work fine. And if we now check the metrics and refresh, we will see that now that we have fixed the memcached, backend traffic is healthy and performant as expected. So this has been a showcase of Hubble. I hope you have understood what Hubble can provide for you and what it can do. If you want to try it out yourself, please do so on the URL on the slide here. We have a getting started guide, which will guide you through a few examples as well. And Hubble, of course, is open source. So please feel free to check out the source to open PRs and issues. So yeah, thanks a lot for your attention and goodbye. All right, so thanks a lot for watching. We do have a few minutes for more additional Q&A. I already tried to answer some during the talk in the chat, but I will now also answer kind of the most common ones here in the Q&A session. If you have more questions afterwards, please feel free to drop me a message either on the KubeCon Slack, or also make sure to join the Cilium Slack. This is cilium.io/Slack especially for more detailed technical questions. So yeah, an answer that came up, or a question that came up quite often is the question whether it is mandatory to have Cilium as a CNI in order to use Hubble, and what this means for things like running Hubble on cloud providers like GKE or AWS. And so the answer is that yes, you will need to deploy Cilium as a CNI to use Hubble. The two are really tightly coupled. However, Cilium as a CNI is able to chain with other CNIs as well. So you can actually use Cilium on top of the GKE or on top of the AWS CNI without problems, and Cilium will integrate quite nicely with the existing CNIs. So Cilium will do things like the observability for Hubble, but the actual pod-to-pod traffic is then handled by the AWS CNI, for example. So yes, it is tied to Cilium, but yes, you can also run Cilium with other CNIs as well. Another question that came up is whether we can also deploy Hubble for VMs and bare metal workloads. And the question here is kind of, or not yet. So Cilium has recently gained, in the latest Cilium release, we have gained the ability to use host firewall rules. So you can now protect hosts using Cilium as well. And this also means that Cilium will get traffic, can observe the traffic on a VM. So this is something we're actively working on in Cilium, and Hubble will gain the workloads as well. Or Hubble will be able to see this. Will be able to see the data produced by VMs and bare metal workloads as well. But this is something that's currently being worked on in Cilium. So yeah, I think the other questions I've already answered in text. There has been a question about security, so I didn't really talk that much about security. It's, of course, you can use Hubble and dump the events in your SIEM or another kind of security focused tool as well. If you have more questions in this regard, please reach out to us on the Slack. I think this is kind of a more detailed question where the use case might be a bit more, where we have to discuss the use case first, whether it's something that is in scope for Hubble or not. But generally speaking, we absolutely also use Hubble for security, observability, especially like the network security policy monitoring that we have in Cilium is one use case that I've demonstrated in the talk. All right. I think this answers almost all questions that we have. I will follow up with the rest here in the platform. And again, please feel free to reach out to me on Slack. This is either the CNCF Slack or also the Cilium Slack. I will be available in both. The channel on the CNCF Slack is the KubeCon Observability channel. And yeah, thanks a lot for attending, and enjoy the rest of KubeCon. Thank you.